Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
All right, let's take a look at our homework for lesson 7.3.2, starting with the M&Ms. And this is the second part of describing association. This is where we're going to start focusing on strength. In the first part of describing association, we were focusing on the kind of the direction of it, whether it was positive or negative or no association. And then the form of it was whether or not it was linear or nonlinear or clustered, and whether or not there were any outliers. Now, let's take a look at these linear models and talk about strength. Okay, so a strong association to your data is when it comes very, very, very close coming to a straight line. Okay, so just think about this. The straight line on the graph has a rule that applies to it. We've been working on this since chapter 2 or chapter 3, right? When we first started with those tile figures of looking for patterns of growth, putting it into a table and putting it into a graph, and eventually creating a rule for it. The closer these dots come in the scatter plot line, that means the stronger the rule that you're going to create for your line of best fit will fit the actual data. Okay, if all of these were perfectly on the line, every single point would be defined by the rule for the line, and you can make really easy predictions after that. But as it starts to get weaker and there are a few points that are straying away from the line, this now becomes more of an average than the actual rule that would fit for the entire situation. Because this point over here is going to be a bit different than this one. So if you use the rule for this, you're not going to get those that are farther away, but at least it comes within the ballpark. Okay, so you start thinking of this. All right, our line is taking on more of a spread here, but it's still relatively close. That's a moderate association. And then here you've got points. I mean, this is only a couple points away from being no association. The moment I add those 4 points, now it's impossible to figure out the trend line. But here you can say, all right, well, there's a flow going in this direction and there's a flow going in that direction. So I think this is basically the flow of the line. And I want to make sure that there are equal numbers of points above it and below it. What does this say? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7. You know what? I would probably actually have my line go more like this. I think that's a better flow to the line than the one that they put. But who am I to judge, right? So anyway, strong association comes very, very close to your line of best fit. Moderate starts to spread out, and then weak gets to the point where you are almost to the point of no association at all. And then, of course, it's negative because it's going in this direction. This is negative because it's going in this direction, and this one is positive because it's going in this direction. And once again, you still got your outliers that you have to be aware of. So this is relatively strong association for a nonlinear positive type of situation. Just remove the outlier and just focus on these. That's your trend. All right, so at a family reunion, each family member recorded his or her age and height. Describe this association fully. Okay, so it's a positive linear association. The person's height appears to be directly related to their age. As you get older, you grow taller, right? But I have to imagine that this doesn't include everybody. I think this might be best if we describe each family member as maybe up until they're 20 years old. Because, when you get to be like 17, 18, 19 years old, you stop growing. And so at that point, you're not going to get anybody. I mean, you're not going to be an 80-year-old who's 20 feet tall, right? That's never going to happen. So, I mean, think about the logic of this. It's definitely positive. It's definitely linear. There don't appear to be any outliers, right? No super tall young kids and no really, really tiny teenagers. And it's not super strong either, right? You see those gaps in between, and they call that, I think they call that the residual, the distance between a point and its line of best fit. And you'll get that in the ninth grade curriculum. So this is moderate, definitely moderate positive linear association with no outliers. Now, copy the scatter plot and draw the trend line. Does your y-intercept make sense for this situation? I have to say, I was kind of surprised when I started teaching this. In my career, I never really had a need to analyze scatter plots, so I didn't really focus too much on this until I started teaching the 8th grade math. But sometimes your y-intercept just doesn't make sense, right? There's no way that you should have a negative height for a person that is 0 years old. I mean, how could there be a negative height? It doesn't make any sense. It seems like the trend line should go from origin through that, and maybe I made it wrong a little bit, but that definitely, this is the flow. And I just need to tell you, follow the flow of the data. You do not, as a researcher, as a scientist, as a mathematician, want to impose your opinions on where you think the line should go. You take the points and you draw that straight line that follows the flow and goes through the center of the data, and you let the slope happen automatically, and you let the y-intercept happen automatically, and then try and describe why that might be the y-intercept. But I'll tell you, this makes absolutely no sense to me at all, the y-intercept. All right, Marissa's older sister was discussing purchasing a car with her summer job earnings. Marissa collected data from her friends at her job. Marissa would like to know the typical age of her friends' cars, what kind of graphical display should be used. And so this, if she wants to figure out the typical age, that's kind of like talking about average. And so in a situation like this, where you're only dealing with a single variable for the data, right? We're only focusing on the age of the cars here. And you might set it up as a box plot so you can get the minimum, maximum, the median, which would be the typical age, right? Another word for average. And then the whole interquartile range could give you a broader sort of a median or a broader average. Marissa wants to convince her dad that newer cars are more fuel efficient. What kind of graph would work for this? All right, now you're trying to see, what does the age of the car have to do with its fuel efficiency, miles per gallon? And so this is this would be what they call bivariate data. Bi meaning two, and variate meaning two different variables. So you got an independent and a dependent variable for this situation, which is perfect for a scatter plot. So we can see the relationship between age and miles per gallon. And maybe we will see a strong association. Maybe we'll see that it's very, very weak or no association. But this is how you would check. So we need to make the scatter plot. And did I make it down here? Is this where it is? Yes, this is where it is. I say that was a weak association. I feel like maybe that should be moderate. I don't think that's, I might change my mind there. Weak negative association, we'll call it weak to moderate. It's certainly not strong, but you do see the trend does go in this direction. So newer cars do tend to have the better gas mileage, and older cars do tend to have lower gas mileage. But I wouldn't say the difference between, they're still hugging in the high 20s to mid 30s, and you got one guy up there that's higher than the rest of them. But still, it looks like a weak association. No, moderate association, but definitely sort of negative there. Well, definitely negative there. So draw a line of best fit for the data and find the equation that fits. Okay. So it looks like our y-intercept, let me get rid of that. The y-intercept appears to be around 37. Put that right there. And then the slope ratio, if we take 2 lattice points on the graph, you figure out that goes down 5 for 8 years. So this is implying that over an 8-year period, the car lost about 5 miles per gallon of fuel efficiency. And so if we change that to a unit rate or a decimal, then it becomes negative 0.625, which could be rounded to negative 0.63, which then you plug into the rule and you could say, all right, a 10-year-old car, what would we expect its gas mileage to be? Or a 20-year-old car, what would we expect its gas mileage to be? Now, what does the y-intercept in this situation represent? It kind of implies that brand new cars on average have about 37 miles to the gallon as their fuel efficiency, right? When x is equal to 0, that means that these are brand new cars. And as time goes on, it appears to lose about 0.62 or 0.63 miles per gallon per year. And then what is this one? The 7-year-old car, where would that go? Plug it in here, or look at your line of best fit, a 7-year-old car. We would expect to have a gas mileage somewhere around 31, 32, maybe, yeah, 31 or 32, somewhere there. All right, looks like a proportional situation. When Malcolm hops 10 times down the hallway, he travels 12 feet. Malcolm. All right, Mr. Hoppy. How many times would he need to hop to travel to his class? He's 90 feet away. You look at him. She's like, dude, seriously? You're hopping to class? All right, I don't make up these problems. I just solve them. How many times it's 90 feet away? We use proportional reasoning. If you wanted to change this to 5/6 and then convert that to a decimal number, 5 divided by 6 is equal to 0.83 repeated. So you could write this as y is equal to 5/6 times x, or y is equal to 0.83 repeated times x. And so solve it algebraically. 12 times 7.5 is equal to 90, so 10 times 7.5 will tell you the number of hops. Or we can take 5 times 90. Let's do this. 5/6 times 90 over 1. So 5 times 90 is 450, and 450 divided by 6 is 75. So you can solve it this way, or use your decimal equivalent, however you want to do it. The answer is 75 hops for Malcolm to get to his class. All right, Jeff and Liz are each saving money for college. Their savings are shown here at the right. Based on the graph, who's saving money the fastest? And if you said Liz because her line is steeper, I would say that is correct. What is the slope of each line? Okay, so let's figure this out. Looking for lattice points, I see there's a lattice point here for Liz, which is at 6,180. And there's a lattice point, which is at 4,120. So it appears as if it goes up 60 for every 2 that it increases, right? So it goes up 2 months and goes up $60. So that ends up being $30 per month for Liz. And for Jeff, where are his lattice points? His started out at 0, and it looks like it goes up to 380. So in 3 months, it increased. Oh no, that was Liz. That's Liz. That's not going to work. Hold on for a second. Right there. I guess right there, that looks like it's 10, right? That's kind of a guess, but I think that's right. So it goes 1, 2, 3 is your change in x, and goes up, looks like from 10 to 80 is 70. So this is increasing by $23.33 per month. Oh, goodness. All right, I'm going to solve one of these. Which one should I do? I think I'll do A. So for A, I'm going to copy the problem down. 1/4 of x plus 1/10 is equal to -3/20x minus 7/10. All right. If I multiply everything times 20, that will cancel out the 4, the 10, and the 20. So I'm going to manipulate this a little bit, and I'm going to say 20 will be like, call that 4 times 5 here, I'm going to call it 2 times 10 here. I'm just going to call it a 20 here, and I'm going to call this a 2 times 10 here. Okay? The reason why I'm doing that is because I know my 4 is going to cancel out with this 4, leaving me with 5x's. I know in this case, the 10 is going to cancel out with the 10, leaving me with 2 times 1. So this expression becomes 5x plus 2 after multiplying both of these times 20. Here, the 20 is going to cancel out, leaving me with negative 3x's. And here, the 10 is going to cancel out, leaving me with 2 times 7, so it's minus 14. So this expression becomes negative 3x minus 14 after multiplying each term times 20. Now, I will add 3x's to each side. I will take away 2 from each side. And then 8 times negative 2 is negative 16. That means x must have been equal to negative 2, which is our solution. All right. If you want me to work out any of these others, you have to ask. Send me an email or jump onto a Google Meet in class time and ask me to work those out. And that's it. We are done with our homework for this lesson. Let's move on to the next activity. Take care.
Hey, feeling good, like I should.